Hello and welcome to the video on exponential functions. We have a number of skill objectives and a couple conceptual objectives. The first skill objective is to evaluate exponential functions. Number 2, graph exponential functions. Number 3, find the domain and range of exponential functions. Number 4, define Eulers number, or what's commonly known as the number E. The fifth one is to solve application problems using exponential functions. These will be things like doubling and half-life problems, and as well as compound interest problems. And then the conceptual objectives. Number 1, understand the difference between algebraic and exponential functions. And number 2, understand that irrational exponents lead to approximations. When we talk about algebraic versus exponential functions, the main difference between the two is the location of the variable. In algebraic functions, the variable will be part of the base. In this case, when we look at x squared and x to the 1/3 power, x is the base of that expression and the constant value happens to be the exponent. And that will always be true when you're talking an algebraic function. When you're talking exponential functions now, the variable is now part of the exponent. Thus, that's why we have 2 to the x power or 1/3 to the x power. The constant is the base, and then the variable is going to be the exponent. Now that we have an idea of the difference between algebraic and exponential functions, let's define the exponential function. An exponential function with base b is denoted by f of x equal to b to the x power, where b and x happen to be any real number, and b has to be a number greater than 0, and b cannot equal 1. If b was equal to 1, it would be a very uninteresting function because we would have 1 to basically any power, and that's not going to change anything. Please note on here, that x is any real number, and as x, the values that we can use for x in a function are called the domain. We know that the domain of an exponential function is going to be any real number. Now let's look at evaluating some exponential functions. The first function we have is y as f of x equals 2 to the x power. And so the first thing I want to do is evaluate. I want to find f of 4. So really, as we've done before, whatever is in here goes in for the variable. So this is just going to be 2 to the 4th power. And if I take 2 to the 4th, I get 2 to the 4th equals 16. So therefore, f of 4 is equal to 16. If I want to find f of negative 2, well then that's going to be 2 to the negative 2 power. Now what we have to remember is when we have a negative power, it means that we can change that to be the reciprocal. So 2 to the negative 2 is going to be the same thing as 1/2 to the second. All we do is we change that base to its reciprocal when we deal with a negative. And so 1/2 to the second comes out to be 1/4. Let's say we have g of x equals 1/4 to the x. Okay, so in this case, I want to find g of negative 1. Well, g of negative 1 is just going to be the reciprocal of that. So 1/4 to negative 1 happens to be equal to 4. The other one I want to find is g of 3/2. Now, when we have a rational exponent, the denominator tells us the root that we're going to use. The numerator tells me what I'm going to do to that value afterwards. So whenever I see one like this, I will take the root first and then the power second. So in this case, I can write 1/4 to the 3/2 power as the square root of 1/4 raised to the 3rd. Well, if I take the square root of 1/4, I get 1/2. And so 1/2 to the 3rd comes out to be 1/8. One thing I would also like you to remember when evaluating exponential functions, if by chance you're asked to go through and evaluate the function at a decimal, then decimal answers are fine. And if you are asked to evaluate the rational function at an irrational number, something like the square root of 7 or pi, you may also use decimals because there's nothing you're going to be able to do to simplify that further than like we could do with the problems that we have on this slide. Now let's take a look at graphs of exponential functions. And we're going to start out with f of x equals 2 to the x. So what I'd like you to do right now is pause the video and go through and evaluate 2 to the x at all of these values here and confirm the results that you see here. Once you do that, then come back, we'll talk about how we go and graph this. Welcome back. I hope that you were able to go and get all those values there. If not, make sure to ask about them in class next time. What happens here is we need to go and graph this. Now, when I go and graph this, I went through and I said, oh, I have the point -2, 1/4. So I went through and I just estimate where that's at. So I have -2, 1/4 right here. -1, 1/2 is that dot. Then 0, 1. That is going to be an important point that you have when you're working with an exponential function. Because in an exponential function, whenever I take something to the 0 power, I will get 1. So when we look at the basic exponential function, they are all going to have a y-intercept, and that y-intercept is going to be 1. The next one I have is 1, 2, then 2, 4, and then 3, 8. So I plotted those out. Now, other things I notice here. Because I have to look at what's happening. Now I can see as I go further in this direction, further to the right, that my function values are getting big and they're getting big fast. In fact, exponential functions are the fastest growing functions out there. There's nothing that grows faster than an exponential function. That's why when we talk about exponential growth, when you hear that term, it actually has a lot of meaning. It means that it's growing very quickly. But let's talk about what's happening as we go off towards negative infinity here. As we go off to the left, I know I'm taking a positive number and raising it to a power. Because I'm taking a positive number, raising it to a power, I know a couple different things. I know it's never going to be 0, because the only way I can ever get 0 when I multiply things is multiplying it by 0. And that just doesn't happen. And the other one is I know it's never going to be negative. There's no way I could take a negative number or a positive number and raise it to a power to get a negative. So therefore, when I look at this, I know that as I move off towards negative infinity, that this graph is just going to keep getting closer and closer to the x-axis, but it's never going to touch it and it's never going to cross it. And so I would say that in this case, my exponential function does have a horizontal asymptote, and that horizontal asymptote happens to be the x-axis. This graph right here, as I mentioned earlier, is exponential growth, an example of exponential growth. What I'd like you to do now is pause the video and make a table similar to this, but instead of doing f of x equals 2 to the x, let f of x equal 1/2 to the x power, and go through and evaluate that. Now, in that table, you can just go ahead and use the values from -2 to 2. You don't have to use 3. And just tell me what you end up, write down what you end up getting, and once you're done with that, come back and we'll go through the graphing of that particular function. Welcome back. Now take a look at, compare your results to what I have in my table. 1/2 to the x. When I put in -2, 1/2 to the -2 power came out to be 4. -1, when x was -1, I got +2. When x is 0, I got 1 again, which is what I should get because I'd have 1/2 to the 0 power, and any number raised to the 0 power is going to be 1. When I put in 1, I get 1/2, and when I put in 2, I get 1/4. Now this function is what's called exponential decay. Now you also need to keep in mind here that 1/2 to the x is also the same thing as 2 to the -x power. So you have to keep that in mind because there is, when we talk about the characteristics here, a lot of times we're going to be talking about what b is, but I'm also going to have you notice the power, the coefficient on the exponent, what happens there. Now, when I plot those points, when I put in -2, I got 4, so I got this point here. When I put in -1, I got 2. When I put 0 in, I got 1. When I put 1, I got 1/2, and then 1/4. Now, I also went through and put in -3, and when I put in -3, I would get a +8. And what happens here, you notice that, again, as we go off in towards positive infinity this time, I'm taking 1/2 to higher and higher powers, but again, I am dealing with a positive number being raised to a power. And as a positive number being raised to a power, it can get closer and closer to 0, but it's never going to equal 0. And it's never going to be negative. So again, my x-axis does come out to be a horizontal asymptote on this, and I am going through the point 0, 1, and this graph here represents what's called exponential decay. Let's talk about some characteristics of graphs of exponential functions. What we're looking at here is f of x equals b to the x. Now again, please notice that the variable has a positive 1 coefficient. Okay, as long as these conditions here in terms of deciding if it's exponential growth or exponential decay are valid as long as the variable has a positive coefficient in the exponent. In this case, the domain is going to be the values from negative infinity to infinity, and the range is going to be from 0 to infinity. Also, the x-intercept, it will never have an x-intercept. When you're looking at something in the form of b to the x, it's never going to cross the x-axis, but its y-intercept is going to be the point 0, 1. Now again, on this one, as long as the exponent has a positive coefficient, and it is positive, in this case positive 1, when I put in 1 in for x, I'm going to get b. So I know this is going to go through the point 1, b, and it's going to go through the point negative 1, 1 over b when I look at that. And as the other thing we have is that it's going to have a horizontal asymptote of the x-axis, which is y equals 0. Now you're going to want to keep that in mind as well, because these are true. All this is true as long as we're dealing with b to the positive x power. The minute we start applying any transformations on this, that is going to change. That will change how this thing works through. So when I start stretching or shrinking it vertically or horizontally, if I start shifting it vertically or horizontally or reflecting it, that's going to cause some changes in some of this part here and even the range. The domain will pretty much stay the same. It will be from negative infinity to infinity. But the range could end up changing if I shift it, especially if I have a vertical shift at all. That's going to affect what that range is. One of the things that we're going to do in class next time is spend some time going through in terms of how to graph an exponential function, just what we need to do, how to go through and locate some points, and identifying the transformations on that and how those transformations affect the graph. But we now know we have a basic idea of what exponential growth and decay look like. We have some basic information, especially the y-intercept, and the fact that the y equals 0 is our horizontal asymptote. And that should be enough to go through, especially if we know our transformations, to go through and get a decent sketch of any exponential function. One thing that is going to make its appearance here, and when we talk about exponentials and logs, which we'll deal with next time, when we talk about these things, we do have a special number. It's a number very similar to pi, in that it's an irrational number, and that is the number e. And the number e is about equal to 2.71828. It is called Eulers number. A lot of people pronounce it Euler, but it's actually Euler. That's one of my pet peeves. So it's Eulers number, and it is one of the values that is very, very important mathematics, in that a lot of things that actually are modeled with exponential functions, actually the base that models them best is Eulers number. So when we look at it, we'll see like f of x equals e to the x is called the natural exponential function, and it has some very similar properties. It's going to go through the point 0, 1. It's going to have the y-axis, the x-axis as a horizontal asymptote. Now, where e comes from? E comes from the analysis of this equation right here. What happens to 1 plus 1 over m to the m power as m gets large? In other words, as m gets very, very big, far away from 0 in the positive direction. And what happens on that is that this thing right there will actually approach what the number E, the 2.71828, blah, 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 that continues on. Let's take a look at an application. We're going to look at a couple different applications of exponential functions. The first one we're going to look at is doubling time or half-life. The doubling time, we're looking above the white line. In doubling time, we have P is equal to P sub 0 times 2 raised to the T over D power. This is your exponent on 2. And in this case, P is the population at time T. P0 is the population when T is equal to 0, in other words, the initial population, and D will be called the doubling time, okay? And when you're looking at a problem that's involving this, they will tell you what the doubling time is. What information you will be given is you will be given the doubling time, you will be given some measure of time, in terms of number of years or days or hours, whatever they happen to be looking at. And they're going to ask, and they're going to either give you P or P0, and they're going to ask you to find the other. It's really what's going to happen. When we talk about half-life, the half-life problem has one change, well, two changes. Notice that the base that we're using is 1/2 instead of 2. We've switched that, which makes sense because in terms of this, we were doubling over here, and now we're doing a half-life. So looking at that. The other thing is, instead of D, which represented doubling time, now we have H, which represents the half-life. So now let's look at an example problem here that deals with one of these, and we're going to actually use the doubling time. We're going to, in this case, our example, in 2004, the population of City A was 10,000 people. It is estimated the population will double in 20 years. What will be the population in 2020? Okay, now when we do this, what you have to recognize here is that the initial population that we're given is 10,000. And so that is going to be when t equals 0. So from this, I know t equals 0 is going to represent the year 2004. And that's going to be something important that you recognize on these things, both the half-life and initial and population doubling. And so, therefore, when I start thinking about the population in 2020, I know that is 16 years after 2004. So, therefore, I know t equals 16 is going to represent 2020. So, putting the values in, I know my initial population is 10,000. So, in the spot where P0 is, I put 10,000. 2 raised to the t divided by my doubling time is 20 years. So to find out what the population is going to be, I replace t with the value of t that represents 2020, which in this case is 16. So I got p equals 10,000 times 2 raised to the 16 over 20 power. At this point, I put this into my calculator and evaluate it. And when I do that, I get 17,411 and some decimal. So different people will evaluate this thing in different ways. Some people, we always sit there and say, we can't have a portion of a person, so it doesn't make any sense to round this to 2 or 3 decimal places. So the question is, do you round it down or do you round it up? And actually, in this case, I will leave it up to you. I will accept either, in this case, 17,411 or 17,412. I typically use traditional rounding. So if it is something that is less than 0.5, I'd round it down. If it's something greater than 0.5, I traditionally round it up. But it really depends on you and the instructor and the courses that you have coming up when they go through and do it, if they tell you to round up or round down. I will say that I'm comfortable either way. Now, the only difference that would happen in terms of a half-life is that instead of the 2, you'd have the 1/2 there, and instead of the doubling time being 20, we would have the half-life being some value. Another type of application is compound interest. Now, you are probably very familiar with these. There are 2 types. One is where where interest is compounded n times per year, and the other is compounded continuously. For those of you who are not familiar with this, when we talk about interest being compounded, it means that it's saying how many times is the interest being added into the account. during the year. So if we are compounded annually, it just means that interest is added one time per year. If it's compounded semi-annually, that means interest is going to be added twice per year. If it's compounded quarterly, it would be added 4 times per year, or basically every 3 months. If it's compounded monthly, it's going to be added in every month. If it's compounded daily, well, that means every day some of the interest is going to be added in. And then the other one we have is compounded continuously. Now, what advantage is that to you? Well, as interest is being added in, that means you're going to calculate it a little bit, your balance is changing. So for the next interest period, you're going to have a little bit more money in there, and therefore you get more interest. So the more compoundings we have on the same interest rate, the better off you're going to be. You're going to actually end up, if that account is going to grow a little bit faster than it would if you only had if interest was only being added in once per year. So we have 2 different formulas for this because we have the 2 different types. Type 1, that first type where it's compounded n times per year, we use the formula A equals P times the quantity 1 plus R over n raised to the nt power. And if it's compounded continuous, and it is only used when it's compounded continuously, I get A equals PE to the RT, or often people remember it as the PERT formula. PERT formula only works when it's compounded continuously. Now, the values, what each variable represents, the A represents your ending amount, what the value of the count after the time period. P is the principal or initial amount that is invested. R is your interest rate. Now, it's important that you remember to write the interest rate as a decimal, and T is the time in years. Now, N, the number of yearly compoundings, is only going to be used for the first type when we're told how many times. You will be told you have an account that's paying 2% interest compounded monthly or compounded semi-annually. Then that's how we know that we're going to be using a value for n, and we use this first type of compound interest problem. Let's take a look at an example here. Nathan has $5,000 to put in a CD paying 5% interest compounded monthly for 10 years. Now, if you're not familiar with a CD, what that means, it's a certificate of deposit. It means that you put it into this account and then you will not touch it for 10 years. And the banks use that because you're guaranteeing that you won't touch it. They pay you a little bit higher interest rate on a certificate of deposit than they do on a standard passbook savings account. So in this case, he's found one that's going to pay 5% interest compounded monthly for 10 years, and we want to know how much will he have in that CD when it matures, so after the 10 years. So because we're told that the interest is being compounded monthly, I know I'm using that first type. So I'm going to use A equals P times 1 plus R over n to the nt power. In this case, pulling from this information, I know my initial amount, which is P, is going to be $5,000. So because we initially have $5,000. Since the interest rate is 5%, R is going to be 0.05. 5% as a decimal would be 0.05. Since we're compounded monthly, I know N is 12. And since it's going for 10 years, I know T is 10. So what I have to do is I'm going to take all that information and I'm going to put it into its spot in this equation. So when I do that, I get A equals 5,000 times 1 plus 0.05 over 12 raised to the 12 times 10 power. Now, as you go through this, I would suggest making sure you multiply that exponent first, because I see a lot of mistakes that happen with people if they just start putting this into their calculator. Because what has to happen is that since this is all part of the exponent, we would need, if you're going to put it like this, without multiplying out the 12 times 10, you would need to put parentheses around the exponent. So when I do it, I just say, well, that's going to be A equals 5,000 times the quantity of 1 plus 0.05 to the 12 raised to the 120 power. At that point, you can put it into your calculator. And when I do that, I get A equals 8,235.047488845, and there's some more decimals that came out on my calculator. So, number one, because we're dealing with money, I'm going to round it to 2 decimal places. So, in this case, after 10 years, I know Nathan is going to have $8,235.05. This does conclude the video for exponential functions and their graphs. Remember, in class, we will look at graphing them a little bit more, and we'll also do another application problem as well. Maybe look at a half-life, talk a little bit about that, and maybe do a interest problem compounded continuously. So with that, I hope you have a good evening, and we'll see you at our next class.